can you discuss an approach to the reasoning about interaction without an actual model? And I think I haven't perhaps been clear enough about this throughout the semester. I've tried to make a big deal about this idea of being able to draw qualitative diagrams, right? So from the beginning, we've been challenging ourselves to draw a diagram and to say, well, if this happens to the input, then what will happen to the height, right? And we've been drawing diagrams like this one, which are qualitative in nature, all the time. Now, this is far and away the least popular part of the course. Every time we talk about this, the thing that people quite like is a quantitative approach, right? So quantitative and let's also call it procedural, right? The qualitative approach is to say, well, I will draw a thing that looks like this, and then I will reason about the behavior of the system, and I will come up with a diagram like this. And this enables me to do all kinds of things, like if I draw some kind of other shape, I can very easily say, well, that's probably going to make a shape like this, you know, kind of second order response. And it's not exact, but it gives me an idea of what's happening. The quantitative version of this, of course, is something like, well, here, you know, step 1, do the Laplace of U, right? Step 2, find the Laplace of G, right? Step 3, Y is equal to G times U. Step 4, find the inverse Laplace of Y of S. And so this is the procedural approach to doing that same thing. And I think perhaps as engineers, we tend to gravitate towards this because it feels like it's the more repeatable, more direct version of the problem. In other words, well, all of these steps are just simple math, and I can get the U, I can get the G, and so on, and then I can get the answer. And the wonderful thing about this is that I don't actually need to know anything useful about the plant itself. And what I mean by that is the kinds of things that we need to know about qualitative control design, in other words, being able to reason about the dynamics of a system, are hard to systematize. They depend to a certain extent on your experience of the world and your experience of real systems and so on. But this kind of stuff bypasses that kind of stuff. So if I have a quantitative approach, I never need a qualitative approach. That's kind of the reasoning, right? Now, to get closer to the question that you were asking, Yakulu, about interaction design, there's really the same kind of idea that if I have a block diagram which features a couple of unit processes, maybe in this, let's say it's in exactly this kind of configuration. If we're thinking about interaction or multivariable control, to a certain extent, some of the interactions are as simple as following the arrows. In other words, we can kind of reason that the material coming in here exits from one of these two positions, and that, you know, the composition of this stream is determined by upstream conditions, but the composition of this stream is not affected by the downstream compositions, right? So there we have kind of rules of thumb in terms of how the interaction works, and you can imagine that the quantitative version of something like this is to have a transfer function matrix, right? So to have some kind of set of inputs and to have a set of outputs. Sorry. So we have a set of outputs and so on, and we can have maybe y2, y1, u1, lots of different inputs, and we can have a full set of inputs here, and then we can do a procedure like the RGA, and the RGA can give us guidelines like, you know, if the RGA looks like ones, you know, that's a good pairing, right? So now we have systems, we have systematized the process of figuring out control couplings. Now, the sad reality is every time we depend on a model, and specifically when we depend on something like a dynamic model, in other words, something that has a Laplace transform or even a derivative or differential equation in it, we are depending on something that by and large does not exist in the real world, in the wild, in process control. And this is a surprising fact about the real world to, I think, quite a few students. The engineering effort involved in developing models for processes means that it is very, very likely that if you have a control system of this kind of size, you know, if you have several units, that you will not actually have any kind of model for that. So at best, you may have, so let's say industrial scale models, right? And perhaps let's make this a little bit more real by talking about a process of the size that's discussed in one of these appendices, right? So let's talk about a process like this one, which is discussed in Seaborg, right? So here we have a reactor, we have a search tank, we have a flash unit, and so on. And now let's dig into what it would require for us to develop a dynamic model of this process. And I'm going to walk through it from the inputs, right? So we've got these two streams. We are putting them into a reactor. Okay, so the first thing that we need some kind of a kinetic model for how the reaction takes place. Very unlikely that we will have good kinetic models, right? Definitely, we will have maybe some kind of idea of what the conversion should be. And I think a lot of people at this point are saying, but wait a minute, if we didn't have good models, how did we do the design in the first place? And again, like the reality is that in many cases, the design of a process like this is done not by using detailed modeling, but rather by doing bench scale work and then scaling up those units, right? So you'd have kind of that kind of a beaker where you have you've added your reagents, you've done some preliminary work on that. Then you have kind of a pilot scale, a big drum with things that you have like with the heating and so on, and then you scale it up. So we've got a couple of scale-up steps, and to a certain extent, by the time we end up with the full unit, right? And if this unit is a large unit, like a couple of cubic meters, it's very unlikely that we have any kind of model for operation. We have running data, but we don't actually have a model. And so, in my experience, most of the time what you have is you have several options for measurement and so on, but you don't really have a very good model. Now you have kind of approximate models for some of these things, and you have designs for these, so you probably have the mechanical details and so on. But each one of these units is designed separately, and nobody really puts together the full model. It's too much trouble to do a full simulation of the full plant, and so you just end up with a partial model. If you're lucky, you have something like a flow sheeting model, so like an Aspen model, typically only steady state. You definitely wouldn't do a dynamic model in most cases, and so part of the plant is built from experience and part of the plant is built from steady state models. But you can imagine that the steady state models, for instance, doesn't even include sizes for these vessels. So we don't know necessarily what the correct operating level should be or what the effective level is on the rate of cooling or anything like that. So there's a lot of stuff that we don't know by the time we put together the model. So how do we do control design when we don't have models, right? So if we don't have these beautiful techniques that we've discussed over here, where we can do quantitative results and do Laplace transforms and RGAs and the like, what do we do instead? Well, it depends on what part of the design process we are. If we are in the design phase, in other words, if this process has not yet been built, the best we can do is to reason through the connectivity of the physical diagram. Now, in a case like this, we know that there's kind of just the flow, all the compositions will affect one another in a downstream way. There are some interesting questions about what the effect of the recycle is, and you'll see that actually, if you read through Appendix G, quite a few of the design decisions that we take are designed to make sure that those effects do not in fact occur. So, for instance, you can say, well, I would like to reason through that this has a reliable effect on that. In other words, increasing A has a reliable effect on the reactor rate or on the reaction rate, which has a reliable effect on the amount of product that I create. But if I have a very strong recycle stream, and if I'm using that for control, I may introduce fluctuations by manipulating this recycle stream. And that makes it harder to reason about how the system behaves. And so instead, I will not manipulate the recycle stream. And I will rather keep that recycle constant, for instance, and make sure that by doing that, if I keep this flow as constant as possible, I'm reducing that recycled effect. So weirdly, on a large-scale control problem, the math is the least important part. It's the least useful tool in your arsenal to understand how large-scale processes work. Now, that's been a long answer, Yakului, but I don't know whether that has answered your specific question. Because in other words, and maybe let me fill in one last blank, is you can, if you want to use a reasoning like the RGA, you can kind of go halfway and, for instance, estimate elements in the gain matrix. Now, when I say estimate, this is kind of the stuff that engineers apparently have nightmares about, right? Like, because I know that I've been asking people, so like, well, what do you estimate this effect is? And most engineering students apparently have not exercised that muscle in their brains at all. So when I say, well, how big will this effect be? What will be that order of magnitude? Few students can give that answer. But that's kind of what you're asked to do, is to say, well, if I were to change the cooling water flow rate, how much would that affect the condensate, right? Going from full open to full closed, how much less condensate will form? This surge tank level, how high does that level get? What's the effect of the level on the flow that goes out, approximately, order of magnitude, right? Like, and many of those things you can estimate. So you can say, well, from all the stuff that I've learned in dynamics, that doubling the height of a tank, for instance, will approximately double the flow going out, depending on the kind of relation, but maybe maximum double, and maybe a little bit less if it's kind of a square root relationship. But if I know the flow at a certain point and I know the level is twice as high, probably the flow will be twice as high or a little bit less, right? So there's an order of magnitude, double, right? It's not 10 times more, it's not 0.1 times more, it's approximately double more. And so you can kind of fill in the gain matrix using that reasoning, right? So you can kind of say, well, so this input has this kind of effect on the output, this input has this kind of effect on the output. And what you see quite a lot in industrial control sessions is when control experts come in, they'll write something on the board that looks like a big version of this matrix, right? So they'll say, okay, so here's U1, here's U2, here's U3, here's all the different outputs. And they'll interrogate this qualitatively. So they'll say, okay, if I do a step in U1, right? If I do a step in each one of these things, what will happen to each one of these outputs? And they'll say, oh, okay, well, U1 has no effect on Y1. But it has kind of maybe like a first order effect on Y2, and maybe that gain is 2, and it has a negative kind of effect on Y3, and maybe that gain is -10, right? And so by filling in this matrix in this kind of order of magnitude way, you're doing intelligent guessing. And so as we saw in semester test 1, like even just knowing the position of the zeros in the gain matrix enables you to make very strong statements about the coupling, for instance, right? Because it's about more than just doing the math. It's about understanding how things are supposed to be coupled together in the first place. This is step 1. And I think this is also kind of a step that students struggle with, because this is very hard to assess in a test kind of in test conditions, right? So the unfortunate reality is that you can't look at a flow sheet like this and understand the control objectives. So when you're talking about what is the thing that I want to control, and you may remember, if you go back all the way to CPN, that's where this subject started, right? The first thing you learned before you started modeling is that we are modeling because we want to control. And we start by understanding the control objectives, right? So if we want to control the level on a tank, we then figure out a strategy. But if that tank is a buffer tank, and actually what we really want to do is control the flow coming out of that tank, we have a different control strategy, right? And the kind of model that we set up also changes based on the kind of strategy that we have. Now, unfortunately, or let's say, how do I know what the control objectives are? And this is a thing that comes directly from the real reason why you have built the plant in the first place. So if I have a thing like this and my goal is to produce this valuable product, we have two very different ways of thinking about that. This same flow sheet admits two different interpretations, right? The one is that I am trying to produce as much product as possible because product costs, or I can sell product for a great deal of money, and I will buy as much of stream A and stream B as I can to maximize the product that I can make, right? And so that's one possible version of this control objective, which is to say, maximize the production of my valuable product. A completely different interpretation, which the same flow sheet, remember, this exact same flow sheet admits that interpretation. Maybe stream A and B are waste streams coming from some other part of the process. And I am trying to either deactivate if these maybe are toxic chemicals, or maybe they are just not very valuable streams, but I prefer to extract some value from them. In that case, my goal may not be to maximize product or production. My goal may be to minimize this purge stream, right? Or it may be to make sure that I use all of the A and B, so that I operate this plant in such a way so that I don't have any A and B that has to be dumped or cannot go into this process successfully, right? So that's the same flow sheet, the same general scheme. And this general scheme is, you may be aware, the general scheme of literally every single chemical engineering plant, right? We have low value chemicals, we make chemistry, we separate out the valuable stuff, we recycle the stuff that hasn't been able to be made more valuable. And that's basically every single flow sheet that you'll ever see in your life if you zoom out far enough. So it's a very general idea. And so you can't simply say, well, this is the way that you do this. You have to start with the objectives. And if your objective is to maximize valuable product, that leads to certain decisions, right? And quite a lot of like these two appendices, F and G, they are really the core of understanding control philosophy, because it tells you that you have control objectives, and most of the time, like every objective that you have in life, you will find that your objectives are contradictory or not all simultaneously attainable, right? So this is the classic, I want to buy a car, but I want the car to cost zero money and use zero petrol, but be infinitely fast and be infinitely spacious and infinitely powerful, so these goals all kind of exist at the same time. These are goals that you have, right? Like you want the fastest car that you can have, you want the biggest car that you can have, you want the cheapest car that you can have. All of those things are there, but you have to play them off against one another, and you find that you can't do them all at once. And so in control terms, what that means is that I have a limited number of degrees of freedom. So I'm trying to maximize product, but I also don't want to blow anybody up, and I want to keep the reactor running, and I want to keep all the levels at the, like just make sure that they don't overflow. And, there's a whole lot of safety requirements. And I have to do all of those things using only a handful of different valves that I can place around the system. And so it's a bit of a balancing act where I work backwards and I say, well, this is the most important thing for me, as I want to produce high value products. So I'm going to measure the product composition. I'm going to operate the flash unit in such a way so that that happens. But the flash unit can't separate out stuff if it hasn't been done correctly in the reactor, right? So I need to maintain the reactor at conditions which lead to that. So those are questions about what things are the control variables and what things do I measure in order to be able to satisfy the control design objective. Right? So we can't see whether we're doing good product if we don't measure the product composition. But if we don't care what the product composition is, and we only care that we're processing all of this, maybe we can save some money by not putting an analyzer in there, right? And then in terms of choosing manipulated variables, so that was choosing controlled variables, right? But then there's choosing manipulated variables. And again, we think about that from availability of the degrees of freedom on the flow sheet like this. But we can also think of it in terms of cost, because adding a valve that is a control valve in over here, process designers are always at odds with process control engineers, because control engineers want to put in very effective valves. Effective control valves have large pressure drops. Large pressure drops in this line means that this pump is going to need to be bigger than it would otherwise have been, which means that the capital cost of the plant is suddenly bigger, right? So there's a subtle interplay between the designers of the physical hardware and the control designers. I'm just going to pause a bit here. I've got a question or a comment here. From a production point of view, I've seen engineers usually take the approach that throughput is always the best strategy to meet your KPIs. Is there a way that we can use the system dynamics and control loops to evaluate if that is actually always the case? Yes, well, that's a very contentious question. So I think the very obvious, let me make a kind of an obvious point. There's always this trade-off between what in mining is often called the grade recovery curve. So if you zoom out and you say you've got raw materials and you've got product, right? Now the absolute best plant that you can design in terms of losses of material, and the best thing that you can do in terms of throughput, is known as a pipe. Right? So if you just build a pipe, you now have a machine that takes all of the raw materials, right, and just in the most straightforward way possible, delivers them on the other side of the plant. And obviously, that pipe is not a good plant. It's not operating well because it's not actually doing anything. It's not actually producing high-spec product, right? So that's the first question. If you do optimization and you say, what's the most direct way to link raw materials to product? If you just want to link those two streams together, you just build a pipe, right? Why is a pipe the wrong way of building a plant? Because we actually have to do transformation. Right? So every plant, every chemical engineering plant, in order to make useful product, there has to be some kind of a transformation. Now, in chemical plants, that's always pretty much always a reaction. Okay? So now we have immediately a question. How effective is this unit operation? Right? What's the conversion of that unit operation? And you can imagine that the conversion, even if it's just a reactor, right, will be different based on the amount of flow that you put into the reactor. And most of you have had reaction kinetics or reactor design, and most of you will know that there is a sweet spot for residence time. If the residence time is too low, you get very low conversion. And so, again, maximum throughput is not the best, right? Because maximum throughput may lead to lower conversion, right? And that's why we then have separation. And the problem is that if I have high throughput with low conversion, all of these intermediate steps get bigger, right? This pipe gets really big. If we push if we have very low conversion, we need a big flash drum, a much bigger flash drum than we would otherwise need if we have good conversion, right? And if we operate this in such a way so that we have less good separation, we may need another separation, right? We may need another reactor, right? And so that's at the heart of design. And now you ask, okay, so we've built this thing. How does control fit into that? Because a lot of what I was just saying seems like a design question, right? And the answer is that we have some kind of target operating condition, right? So let's say that's a reactor that operates at a particular temperature and pressure, right? And we've done our Aspen simulation and we figured out that the absolute best place to operate is over there. That's where the conversion is maximized, or that's where this plant is designed to operate. The problem is that these raw materials, these streams typically look like this, right? So there's no raw material that is perfectly pure, or there's no particular, even if that raw material was like that, the ambient conditions change and so on. And so what actually ends up happening is we operate at some point that is away from the ideal operating point. And in the single variable version of this, we may want to operate at some target pressure, and you know, the way that these things typically work is that actually there's an upper bound on that. You know, almost all of the time, those things are bounded. So, you know, the best operating temperature and pressure is often the highest temperature and pressure, or there's some other operating constraint. And if we can if we have two different versions of events, one where we have high variance and one where we have low variance. Let me use a different color. If something bad happens when we reach that bounding pressure, the system with the lowest variance allows us to operate more closely to the optimum operating conditions, right? And so having good control and having controllers that are automatically figuring out what the best operating conditions are is why good control is good for business. It's why we get more on-spec product if we have good control than if we have bad control. It's also, you know, this kind of oscillatory behavior or variance behavior is, for instance, one of the reasons why we don't like manipulating recycles, right? So I don't know whether that's answered your question in terms of this, but if the KPIs are chosen correctly, in other words, if the KPIs align with the control system design, and if we are truly interested in producing, maximizing production of on-spec product, then we will operate the whole unit in such a way so that we minimize downtime, we minimize variance, we operate near the optimum conditions, and we have a control system that supports us in that goal. If any of those things don't happen, then the other things don't happen. In other words, if we have a control system that is difficult to use, it means that in order to be a little bit more, let's say we know the control system often gets things wrong. So we'll rather than put the set point somewhere here in the safe area, right? Which is we're not operating at an optimal condition, but we're further away from the place where things go wrong. And so in many cases, what you'll find is that systems are resilient They don't necessarily blow up. They just operate at some suboptimal condition. Did that answer your question? Yeah, I think the specifying the control design objectives, you can actually think about this in terms of all of the steps that are mentioned in this appendix, right? So we've got the system objectives, and those system objectives are typically informed by business, right? We built this unit in the first place because we had some kind of a business goal, right? Nobody just builds a plant. We build a plant because there was a gap in the market, and we had to either produce the product or get rid of get rid of waste streams or do whatever. So these things are actually kind of externally imposed. Then we have these kinds of constraints, and these constraints are typically hard constraints in the sense that you can't really negotiate safety limits. You can't really negotiate away the pressure limits of a vessel or anything like that. But this forms the boundary of the design, and actually, and you'll see this in the book as well. For as long as I've been teaching the subject, every textbook that I've ever used and every person that I've ever spoken with agrees that control design should be done simultaneously with process design. So they'll say something like, well, the reason why this thing is difficult to control is because the flash unit is undersized, right? Like it was designed with a too small sump, and therefore we can't actually absorb the kind of changes that we want to change. But the real problem is this thing that I spoke about earlier, which is that probably this flow sheet was designed from a completely steady state point of view, right? So because that's a steady state, because the design was probably done with steady state assumptions, when you make steady state assumptions, none of the vessels have any capacity, right? And so when you then try to size them, you use some rules of thumb, but you're very strongly motivated to reduce the capital cost of that plant. And so you put in a too small flash unit, you put in too small pumps, you put the lines are undersized, the valves are undersized, and so on, because you're trying to minimize capital cost, and the control guy hasn't told you that actually it would be great if we had some extra capacity in the sump of that unit. Actually, it would be great if we had a bigger pump so that we could put in an effective control valve. Usually how that works even now is that there's a back and forth. So the process designers design it, and then you get this flow sheet, and then you have to actually add control. You're doing the thing that you're doing now in the control project, right? So you get a flow sheet already optimized by very clever people who have done optimization, and they've shown that the new flow sheet is 20% more effective than the old flow sheet, and it's process integrated and so on. And then you have to tell them that, wait a minute, that process integration means that things are a lot harder to control, and you have to fight back. If you're doing this rationally in a big team, everybody is involved at the same time, so that when you make that mechanical design decision, the control person can say, no, that doesn't seem like a good idea to me. And then there's this higher level thing, which is what you alluded to earlier, which is that none of the control system or the plant works well if the people are turning the controllers off. And so you also have to align the incentive schemes that you have so that they are well chosen. And this is a bit beyond the scope of the module, but it's worth keeping in mind. When I had just started at the university, one of my colleagues was working at a smelter, and he told me this wonderful story, which is that the way that mines work is you take big rocks out of the ground, right, and you mill them, you break them down into smaller rocks, right, into smaller rocks, and then you have another mill, and then you get something like a slurry, and then you have a whole lot of different metallurgical processes, and in each of these processes you're extracting out some valuable stuff. And this, in metallurgy, they talk about gangue. This is like So, and there's kind of gang in each one of these steps, right? So you're taking out, in this case, they were taking out tin, Sn. So it was a tin mine, right? Okay, so they were taking out the valuables, and then at some point they said, you know what is amazing? Incentive schemes. We're gonna say that the unit, so each one of these processes is a unit, and you can see that in most cases this is kind of how it works. Is like you have the primary milling unit, and then you have the secondary milling unit, and then you have a unit that does some kind of hydrometallurgy, and then some other hydrometallurgy, and so on. And you've got these different units, and they said, okay, the unit that has the best year-on-year improvement in their yield, in their throughput, they get a BRI at the end of the month. And what they found was that one of these downstream units, so this guy was saying that they had invested in building a fence around their unit. Right? They'd taken some of their R&D money and built a fence around their unit. And the reason is because one of these downstream units had taken their money and invested it in a front-end loader that they could use to take the pile of gang from here and bypass this unit and put it into that unit. And so this is a classic example of what is also called the Cobra effect, or there's a couple of names for this. You can go and look at this. So there's a Cobra effect, and there's also, you can look at rat tails, which is a reference to people paying bounties for rat tails or cobras. So like you have a snake problem, you want to make sure that people catch a lot of snakes. So you say, we'll pay you for snakes, and then, we'll pay you for tails of rats because we have a lot of rat problems and we want people to kill rats. And then what happens is people start cobra and rat farms, because then they realize that they can actually be paid, because they don't actually have those same goals. They don't have they don't have the goals of the larger plant in mind, right? They just want to have a BRI, or they just want to get the money from the rat tails. And so it's very important that when you choose your KPIs, when you choose everything, that everybody is aligned. So on a large scale, when you think about these alignment projects, when you think about safety goals, when you think about environmental goals, if you lose that, if you have an environmental target, but it is unimportant to the people working on the plant, you will immediately start seeing people trying to bypass it. You'll start seeing people putting coins in fuse boxes and balancing stuff to acknowledge alarms and so on. So actually on this higher level, you realize that to a certain extent, it doesn't really matter whether the PID controller is tuned properly. The main challenge of a control engineer in practice is often just to stop people from putting the controller in manual. Something like 2/3 of controllers have been found to actually make control worse. And largely that is because they're being used incorrectly. Part of it is because they're being tuned incorrectly, but also part of it is just that people turn them off and prefer to just control the plant manually. So it's a really tough question. Yeah, like you say, Goodhart's law is another one to Google. By the way, while we're talking about this and control as well, what does this all have to do with control? Is if you have gone through this module the way that I have tried to present it, right? It is my goal that when we started this discussion about plant-wide control, or when you started looking at the ways in which we address plant-wide control, your immediate impression should have been, wait a minute, this is why we've been spending so much time on this qualitative stuff. This is why it's important to be able to predict how a controller will behave. This is important why it's important to predict how a piece of a system will behave. This is why it's important to predict how connected systems will behave. Because eventually, right now, we are not in a place where we are able to do this completely automated. It's to remove the mechanical work and allow you to focus on the qualitative work, because I believe that's really where you're going to be spending most of your time. Now, at the same time, I also believe that by the time most of you are going to be working, the technology will have, gone a little bit further. But if you're working in South Africa, you'll be working on plants that are 30, 40, 50 years old. And so it's probably quite useful to know a little bit about the design process of 50 years ago when you're working on a plant that was designed at that time. And trust me, I've been working on industrial projects, for longer than most of you have been alive. And these things do not go away. This is a problem that we still have, that these things, that the industrial scale models do not actually exist. Large scale, dynamic industrial scale models do not exist for most plants that you're going to work on. And so you're always going to have to be back on qualitative, right? And it's really once you start, but if you don't understand how those low-level things work and kind of the failure modes in which they can fail, if you don't understand like at least what it is to tune a PID controller, those things have to be in place for any of the rest to make sense. So if your PID controller doesn't work at all, it's kind of useless to have a very intricate high-level control strategy, because you're always just going to be fighting against this variance, right? You're just going to be trying to figure out how to operate closer to that point, and you're not going to have the mental energy to actually figure out the correct optimal operating point. And there's a whole world, there's a whole set of subjects. If you are interested in control, the postgraduate course in control is really where you will start to understand how all of this actually starts getting rolled out in the real world.